Hi, everyone. So why is it that as polar coordinates, r equals 2 sine of theta graphs as a nice circle? Well, Desmos says so. Desmos is good at graphing r as a function of theta as polar coordinates. But even then, Desmos fails to put the arrow indicating orientation. Bad Desmos. But Desmos knows that we get a circle. How can we know that? Let's look at this analytically. First of all, is the pole, or origin, on the graph? Well, the pole corresponds to r equals 0. Is 0 in the range of 2 sine of theta? Does 2 sine of theta hit 0? Yes, it does. For example, when theta is 0. So the pole is on the graph. 0 is in the range, the pole is on the graph. From now on, let's assume r is not 0, and we can multiply both sides by r. R times r is r squared, and then equals 2r sine of theta. Now remember, how do we convert from polar back to Cartesian? What is r squared in Cartesian, and what is r sine of theta in Cartesian? Remember, r squared is x squared plus y squared, and y over here is r sine of theta. R squared is x squared plus y squared equals the 2, and then r sine of theta is y. I'll do this in red. R sine of theta is y. All right, so we have x squared plus y squared equals 2y. Okay, now let's subtract 2y from both sides. Let's get this to the standard form of the equation of a circle. CTS. We group these terms together. Use CTS by adding 1, completing the square by adding 1. If you add 1 in here, you have to balance that out by adding a 1 to the right side. Fortunately, we just have a 1 out here, not a 2 or a 3. So we add 1 to both sides, basically. All right. Factor the PST here. We get x squared plus the square of y minus 1 equals 1. That's the standard form for the equation of a circle. What's its center? What's its radius? For the center, what makes the left side equal to 0? 0, comma 1. What's the radius? R squared is 1, so r is 1. So here's the data. We have a circle of radius 1 centered at 0, comma 1. A circle centered at 0, comma 1, and the radius is 1. In Cartesian, it might look better. All right. However, this analysis does not indicate orientation. This process is sometimes called eliminating the parameters. But one problem with that is that you sometimes lose orientation. This tells you nothing about orientation. Remember that in our class, it's going to be counterclockwise. Put the arrow in. All right. Now, in example 2, let's look at how to graph r equals negative 2 sine of theta as polar coordinates. Well, it's a similar process. Now, if you first graph r against theta as Cartesian coordinates, you get the good evening graph here, right? And then, as theta goes through quadrants 1 and 2, what happens with the actual particle or the actual curve? Well, when theta is in quadrants 1 and 2, where do we graph? R is not positive. R is negative in here, right? R is negative. So we don't graph in quadrants 1 and 2. We graph in the opposing quadrants. We don't graph in quadrants 1 and 2. We graph in the opposing quadrants. The opposing quadrant for 1 is quadrant 3. And the opposing quadrant for 2 is quadrant 4. So in phase 1, we graph in quadrant 3. In phase 2, we graph in quadrant 4. And by the way, why is this south pole point on here? 2 units below the origin or pole. Well, that corresponds to theta equals pi over 2. When theta equals pi over 2, r is negative 2. All right. So when theta equals pi over 2, we graph this way if r is positive, but wait, if r is negative, we graph in the opposing direction. That's probably better to say than the wrong direction. We graph in the opposing direction. We graph in the south direction. The point is 2 units or 2 meters maybe south or below the pole. All right. And then in quadrants 3 and 4, well, r is positive here. We are graphing in quadrants 3 and 4. It turns out that we're just retracing our steps. Phase 3 retraces phase 1. Phase 4 retraces phase 2. Remember to put at least one orientation arrow. Using polar graph paper, looks like this. R equals 0, and then r goes towards negative 2. If r is negative, so we're not in quadrant 1, we're in quadrant 3, right? Until we hit the south pole over here, all right? And then in quadrant 2, again, r is negative, so we're actually graphing in quadrant 4 again. We're graphing quadrant 4, all right? In quadrant 3, when theta is in quadrant 3, r is positive, we are graphing in quadrant 3. And when theta is in quadrant 4, r is positive, we are graphing in quadrant 4. We're just retracing the steps. So I'm going to have you graph circles, but the graphs do get more complicated and more beautiful, as we'll see.